Okay, so good afternoon. We are still handling the people that are joining. Okay, so I'm Filipe Soares. I'm with INESC TEC, and I'm the moderator of this session with Micael Simões and Bálint Hartmann. The session will be about, the title is Navigating TSO, DSO Operational and Institutional Challenges. And we will have here two testimonies that are quite, they are linked because they address the same topic, but they are quite different. One is more technical, one from Micael, where Micael will present how he has, during the last years, been tackling the changes of operational management between TSO and DSO. And he will present some results and some potential solutions to overcome the burden of the interaction between DSOs and TSOs. On the other hand, Bálint will present a series of studies showing the interaction also between DSO and TSO, and the burden that it is to communicate between these two hierarchical levels of the power system. So the first one will be Micael. So Micael is with INESC for many years now. He's a PhD student finishing his PhD. So right now, so he won't be a PhD student for much longer. He has a quite extensive experience in European projects, for instance, where he developed several tools, including some open source tools, addressing precisely the issues of the cooperation between TSOs and DSOs, both from an operational perspective, but also from a planning perspective. So in terms of software, is very experienced, and I think we can start with your presentation, Micael. For the audience, so just a moment. So for the audience, you have the Q&A button that you can just drop your question. We'll have both presentations first. And then, I don't know, 20 minutes, around 20 minutes, each presentation. And then you can drop your questions in the Q&A. And then at the end, we will together moderate the questions, and we will interact with Bálint and Micael. Okay, Micael, the floor is yours.
Okay, thank you for the introduction as well. Let me share my screen. I'll be presenting some of the work that we've been developing within this TSO-DSO coordination topic. The presentation is titled TSO-DSO Coordination, Fostering Demand-Side Flexibility for Optimal Operation of the Overall Power System. This is the outline of the presentation. First, we'll go through the motivation for the adoption of this type of coordination mechanisms. Then we'll present the most popular coordination mechanisms proposed in the available scientific literature, and then we'll go through the main contributions of this work, namely a new TSO-DSO coordination mechanism, and then we present how we implement this in practice through an operational planning tool, and then we perform a comparison with other coordination strategies proposed in the literature. Finally, we conclude and point towards future research directions. So now talking a bit about the motivation for the adoption of this type of coordination mechanisms. Electric power systems are currently experiencing a very profound change with the connection of large amounts of renewable energy sources at both transmission and distribution network level, which are starting to displace conventional generators, which are nowadays essential for the operation of the power system, and at the same time, the connection of large amounts of distributed energy resources at the distribution network level. However, currently there is little to no interaction or information exchange, especially in operational planning settings, between TSO and DSOs, which leads to this flexibility, this growing flexibility at the distribution network level is currently not being shared with the overall power system and therefore not benefiting the overall power system. And so the way TSOs and DSOs interact with each other will have to change. And so in this regard, several TSO-DSO coordination mechanisms have been proposed to effectively and efficiently share this flexibility from the DM side to the overall, with the overall power system. Regarding TSO-DSO coordination mechanisms, especially those proposed in the literature, this can be classified into main types, where global markets exist, that is, all of the resources in the network, both transmission and distribution network levels, participate in a single market, and these are typically solved through co-optimization methods or global optimization methods, and decentralized schemes, essentially where local markets exist, that is, resources connected to the transmission level have their own market, and resources connected to distribution networks have their own markets, local markets. And this can be solved through two main types of solution methods. Hierarchical optimization that follows a typical leader-follower organization. In this setting, typically TSOs perform local decisions based on their own network and then communicate their own decisions to TSO, which optimizes the system-wide, taking into account these decisions from distribution system operators. And so this is a sort of a unidirectional information flow. On the other hand, distributed optimization methods, essentially the big problem is decomposed into smaller subproblems, and TSO and DSO need to agree on coupling variables. In a TSO-DSO coordination setting, these are typically active and reactive power flows between transmission and distribution network, voltage magnitude at interface buses, and so on. And so in this setting, we sort of have a bidirectional information flow. And so what do we propose here? We propose a distributed coordination scheme. And here the main novelty is that we consider shared resources installed at the interface between transmission and distribution network. And here the main idea is that these resources can not only provide additional flexibility for the operation of the network, either it is transmission or distribution, but especially that it improves the efficiency of this coordination procedure. As I've noted earlier, TSO and DSO need to agree on these coupling variables that are essentially variables that represent the interface between transmission and distribution network. By installing this type of resources, in this case, shared energy storage systems, at precisely these points, we believe that we provide additional flexibility that can improve the coordination procedure. And with this, what our main goals is to preserve the data privacy of the system operators, and therefore compliance with current regulation, that is transmission and distribution should be unbundled, and also the tractability of this very large scale problem. And how do we implement this in practice? Essentially, we propose a consensus-based residual balanced alternating direction method of multipliers, where we consider the coupling variables to be active and reactive power flows between transmission and distribution networks, and also a voltage magnitude at the interface buses, and also the power and reactive, the active and reactive power from the shared energy storage systems installed at the interface between transmission and distribution systems. How are the network, the operator's network management tools implemented? Through stochastic multi-period optimal power flows. Here we consider the exact power flow model with voltage represented in rectangular coordinates, We consider uncertainty from market price forecasts, that is wholesale energy flexibility market prices, and operational forecasts, that is load and renewable generation. And we accurately represent several types of resources, that is OLTC transformers, capacitor banks, energy storage systems and renewable generators with reactive power support, shiftable loads, that is loads that maintain their energy balance throughout the optimization period. Here, the main objective is to accurately assess the potential of active distribution networks to provide flexibility services to system-wide operation. As many of you know, typically in this type of problems, large OPF problems, the network power flow equations, for instance, are approximated or linearized or convexified, which can many times lead to inaccuracies in representing this ADM's flexibility and therefore reliability and even security problems at the transmission level when considering flexibility from active distribution networks. So we conducted a few case studies. The case studies are based on standard IEEE test systems. For the transmission network, we adopt the 9-bus transmission network system. For the distribution networks, we adopt the 33-bus radial test system. And the case study is conducted for a period of high renewable generation where small bus voltage violations are observed at the transmission network level. And we compare traditional, that is uncoordinated operation between transmission and distribution network, centralized optimization, that is the whole network is optimized as one, that serves as a benchmark for comparison purposes with the TSO-DSO coordination mechanisms proposed, a hierarchical mechanism where we represent the ADNs through equivalent PQ maps or flexible operating regions, and with our proposed distributed approach, considering and not considering shared energy storage systems installed at the interface nodes. Here we can see the examples of the FORs or PQ maps that we developed. As you can see in this, you can see for several partition levels. And as you can see, the higher the partition level, the more accurate you can represent the boundary of the polygon representing the active and reactive power flexibility of an active distribution network participating in this coordination scheme. And so now some results for a single period optimization. The main takeaway here is that all of the bus voltage violations observed in non-coordinated mode are solved through coordinated operation of transmission and distribution network. Centralized optimization naturally achieves the lowest operational costs. And here we can observe that the problem of scaling is really not noticeable. In fact, it's quicker to solve than the uncoordinated case. This is probably due to the fact that it's an easier problem to solve when you have access to more flexible resources. Among the decentralized schemes, that is hierarchical and distributed schemes, the distributed schemes achieve the best results. Hierarchical schemes actually, despite solving the voltage problems, lead to higher operational costs. Distributed schemes actually solve the voltage violation problems, but decrease the operational costs overall. And interestingly enough, they are computationally less expensive than the hierarchical schemes. Now extending this analysis to a multi-period case study, once again, all of the bus voltage violations observed are solved through coordinated operation of transmission and distribution networks. Centralized optimization achieves, once again, the best results in terms of operational costs, but we can see the problem of scalability here. Compared to the previous test case that took around half the computational effort to solve, here it already takes 72% more effort compared to the uncoordinated test case. Among the decentralized schemes, the distributed schemes achieved once again the best results in terms of operational cost, but not necessarily in terms of computational effort. That is, without shared DSSs, it's quicker to solve than all of the hierarchical test cases considered, but when shared DSSs are considered, it is computationally more expensive. This once again highlights that there is probably no one solution that fits all use cases. And so now to conclude, we propose a new TSO-DSO coordination mechanism where here the main novelty is the integration of shared resources that can be exploited by transmission and distribution system operators. And we've shown that it can bring several benefits to network operation, namely in the effectiveness of the coordination procedure. We propose a stochastic multi-period optimal power flow that is accurately modeled, and it was actually tested in a lab environment through power hardware in the loop simulation where it was validated. And we propose a coordinated TSO-DSO operational planning tool that brings several cost and operational benefits, namely, in this case, solving voltage violations at the TN level, and that is not necessarily more computationally expensive than the most popular approaches available in the literature, namely PQ maps. It does, however, require more communication rounds between system operators, which might be the biggest hurdle for their practical implementation. That's it from my side. Thank you.
Thank you, Micael, for your presentation. I guess that we can pass now to Bálint. Okay, a few words about Bálint. He's a senior research at the Budapest University of Economics, and also the Center for Energy Research, which I think is linked to the university. He is also a founder of the FASTER, which is a company that focuses on static and dynamic behavior of power systems. His research is or has been focused on the integration of renewables, also integration of storage, machine learning applied to power systems, and multi-energy systems in general. He has a very extensive experience in the topic. He has published more than 20 papers, and he is also very active in several R&D projects, both at national and international level. And he was the chair of the IEEE PES Hungary chapter between 2019 and 2021. So, Bálint, this is a very short introduction to your CV. You have quite a lot of experience, and okay. So now you can start your presentation. If that's okay.
Thank you, Filipe.
You can. Okay,
you can see me. All of you, I'm going to quickly share a screen. Please give me a response that you see it actually.
It's working. It's okay.
Perfect. Thank you. So once again, good afternoon to everybody who is attending this webinar. I'm very happy to be here, and it's going to be a bit different presentation than the previous one. I'm going to be a bit less on the technical side and maybe a bit more on the institutional side, and just going to pop up some ideas about what we're doing wrong, maybe in our power system expansion planning and how we handle the different development plans. Everything that we're going to say today is our collaborative work as usual with our research group. For this specific presentation, I had great contributions from Peter and Balázs. Balázs, in this case, is also working with Mobil, the Hungarian TSO, so is providing good insights into the things that we like to get curious about. So without further ado, let's just jump into it. You might all know, I guess, expansion planning, how it works and why we are doing this. the most important thing I believe about this topic is that it's obligatory. In many cases, if you have to do something because you must do it, it's not with enthusiasm and you try to handle it with minimal effort. I'm not saying that this is true for the TSOs, but in general, this is the experience of engineers, I guess. But nevertheless, we have many binding directives, actions, and laws different on the different countries that are doing this process. Most importantly, we have EU regulations that are shown here, which are more or less describing the methodology of expansion planning and also how the results could be shared and how we harmonize it on the European level. Now, nevertheless, this is also the experience of the different TSOs, how they do it and how their ideas are incorporated to the TYNDP of ENTSO-E. But this is still just a plan. And as usual with plans, they might fail, and in many cases they do fail. I've cited a few examples from international studies and look backs from these years. We have the TYNDP from 3 years ago, and it was said that 40% of the planned transmission investments faced delays in the 2 years prior. So this was just right after COVID or during the COVID rebound. And also they stated that 12% of the European project remained in a so-called prolonged permitting phase, which is going to be called in this presentation as carryover projects, which means that instead of delivering the projects on time, it's going to remain in the pipeline for multiple years, in some cases even for a decade. And this is certainly something interesting to look at why these projects are existing. We also have another review from Acer from last year. They were examining the PCI projects. So again, projects of common interest, highest importance projects in the European Union, and still 30% of those projects have experienced delays in the previous years. The reason for that was multiple. Shortage of manpower, shortage of units to be built in, permitting issues, legal issues, etc., etc. But nevertheless, it was seen that on the European level, we are experiencing this issue. And also just to go to the other side of the ocean, here's an example from the States by the INESC Center think tank. They reported that in 2024, 11% of projects on transmission level were canceled, which were in the pipeline. And also they reported a quite long federal permitting phase. On average, more than 4 years were spent waiting just for the permits. And the longest permitting time that was actually reported was 11 years. So again, as you might see, we expect those plans to fail, but again, the failure rate is quite high. And we got to ourselves and got thinking, and we had 2 or 3 hypotheses and 2 research questions that my presentation is going to go around. How do we explain these repeated timeline shifts? What is the reason? Is it institutional? Is it because of the NDP's methodology, what the TSOs are using, or is it just because of the political or economical environment? And also to understand how this works, of course, we have to also check how the plans evolved over time. Now, first things first, we wanted to look into other papers, academic literature, discuss with other TSOs, whether they have looked into the topic, and we did not really see any systematic overview of this issue. So we leaned to another field, and we try to encapsulate all this thinking within something that we call the institutional drift. This idea or this theorem was introduced a little bit more than 20 years ago by Kathleen Thielen and her colleagues. And the idea of this is shortly explained here, saying that institutional drift refers to a situation of changed impact on existing institutions because of the shift in the institution's environment and a lack of adjustment to them. Shortly, how we summarize, we have the same rules for many years, but we have different outcomes of the same process. And we are curious about why this is. Certainly, TSO expansion planning is not a typical institutional drift because it's not only a single institution, we have many regulated entities. But if you look on the right side and check the framework, how we can explain the drift, there are 2 things that might pop out. The characteristics of the political context, which in all of the cases are also having a huge impact on the TSO's plans, and also the characteristics of the institutions. So expansion planning is typically shifted somewhere between DSOs, TSOs, also the regulator is involved, so it's a regulated process, and in many cases regulated processes tend to be slow and tend to have delays. So we try to get the data set together and see how institutional drift could be seen in this data. Before jumping to the dataset, just to provide a short insight to what the Hungarian TSO MOVIR is doing, you can see that in the last, let's say, 15 years, we had 4 slightly different periods of how the network development plans were handled by MOVIR. We had a period before 2010, then for 8 years we also had a consistent methodology. Then we had a huge structural reform and content-wise reform as well of the NDP in 2019 and 2020. And after 2021, the ongoing model is seen. And while we have tried to show you the differences between those 4 eras, it has to be emphasized that this is still a TSO-led process. Of course, the distribution system operators are providing some insight to it. And of course, there's a lot more discussion ongoing between the different stakeholders than 15 years prior. But still, the final say is what the TSO is going to say. And also the plans are jointly published by the TSO. So we can say it's still a TSO-centric plan. The other thing that we know, again, also thanks to the insight and discussion with MOVIR's colleagues, that despite the fact that we increased the number of scenarios to be checked in the simulations, we have involved new technologies like, for example, battery systems. We are trying to incorporate various means of smart systems into the network planning process. The core is still load flow calculations, short circuit calculations, and things like that. So I would say that we're not expecting very different results at the end of the process. The input information and the focus, so how we, how we tell the narrative of this whole plan is different, but the tools are the same. So again, same rules should lead to more or less the same outcome, but it is not like that. Considering the data set, we have set together 15 years of Hungarian NDPs from 2010 to last year. And we have included all those planned investments that were listed, which came up to about 900 plus investment projects in 15 years time. This is already after pre-processing and filtering some of them that were duplicated or became obsolete for some reason. First, we try to create some simple flagging. We generalize whether they are planned by the TSO or the DSO, whether it is a new element or an upgrade of an existing one. And we also use 3 different categories for the type of the gear or the unit that we're talking about, whether it's a new or upgraded substation, whether it's upgrade of a power line, or whether it's some kind of auxiliary device, like, for example, installing shunt compensators at the TSO substations. After that, we have 900 rows of projects for 15 years. So this is 900 times 50 metrics that we can analyze. And we did it 2 different ways. One is what we call the project focus metrics, which is analyzing each of those investments one by one. And we're trying to look into the, for example, the initial lead time of the project. So how many years are we waiting until delivery? What is the trajectory of the commissioning date, etc., etc. But we're also looking for the cohort focus metrics. So the data seen in a given year also telling us something about methodological changes, about the environmental changes and things like that. So we're also trying to check, for example, what was the survival rate of projects included in the NDP for a given year. And I'm not going into very much of the detail of the statistics because we have a lot of data. But again, this is brand new, hasn't been published. So I'm just trying to put as many quick facts and figures on the slides as possible. So just 4 short statistics. The initial lead time, so when the plan enters, so when the investment enters the plan and the expected commission date is somewhere around 4 years. So we're planning 4.5 years in advance. And as expected, the TSO's investments are taking a little bit longer, but we don't really see a huge difference here. Then we checked the relative changes in the operational date, which means it is 100% if the expected operational date is changed every year. Now you can see that for all the 900 investments, we have it almost at 50%, which means that all of those projects on average are changed every second year, considering their delivery date, and definitely the DSO is a forerunner in this case. But still, for the TSO projects, every 3rd year we change the planned commissioning of the given investments, with it again telling us a lot about how how fluctuating this whole process is. Then we have something that we call the cancellation log. So we include something in the plan, but it's never going to be built for some reasons. For example, we have installation request for a new power plant, but for some financial reasons, it's never going to be realized. But still, the TSO includes them in the plans, and of course, other elements of the power system are going to be planned respectively. In this case, what was striking to us that for the DSO, we have only about 1.7 years spent in the plan before removing them from the plan. So again, a very fluctuating set of data what we have here. And last but not least, we have the completion rate. So out of those 900 investments that ever entered the plans, only 40% of them has been finished up to date today. I'm going to emphasize this because of those 900 projects, approximately 1/3 of them is still to be delivered. So they have the chance to increase this rate to somewhere around 30% expected, but still it's a very low rate. And if you compare how the TSOs and DSOs perform, definitely it's the DSO side that is causing the issue with these numbers. Let's just jump into the other type of analysis, so some cohort-focused metrics. We have filtered these 900 projects to two categories, or at least those two I'm going to present to you today. The first one is the project that have spent at least 10 years in the pipeline. So these are really strategic investments for critical infrastructure, and they have been planned in some cases even before 2010. So they were already on the National Development Plan from that year. And for each of these cells, you can see how the status of the project was changed. If it's red, it has been delayed with 1+ years. If it's green, then it's gone as planned. And if it's yellow, it's gone as planned. And if it's green, then we have advance in the project, which means that the delivery date has been brought to a shorter horizon. Now, 10 of those projects here, you can see that most of these cases, they were delayed. We only have a few cases when they were advanced, and even of those projects, 2 of them were never realized. Despite having advanced status in 2 years, but still, in 4 of those years, they were delayed. And as you can see, there is some kind of a pattern showing here that if you have to delay something every second year, it might not be realized at the end. On the other hand, we have some better examples or more stable investments. For example, these two with the TSO connected to the same type of infrastructure. That's the reason why they have the same pattern. They were only delayed once during their lifetime, and they were delivered approximately on time for the final expected delivery. And now we have also 2 examples which are still included in the plans. They are yet to be built, but it's also telling that for the DSO, we have at least 5 years when the project was delayed, and it's still in the pipeline for 10 years. So it's quite interesting to check one by one on these projects what is causing the delay. And another category that we filtered is projects with 5 to 9 years in the pipeline. This is even a lot more. On the left side, you can see TSO projects. On the right, the DSO ones. 2 things to be clearly noticed. On the DSO side, you have a lot more delays. So approximately, if you check the share of reds in this figure, it's somewhere around 75–80% when those projects are delayed. And of course, these delays are having an effect how the TSO is planning the infrastructure, because they simply don't really know what to rely on the 132 kV side. The other thing that I would like to highlight, and it's a lot more related to this institutional drift, is the year 2019 and 2020. Here, as you can see on the DSO side, we have many projects that were advanced. And also the same shows here on the TSO side, 3 advanced projects with 3 delayed and 4 planned projects. This was the year when the methodology of the TSO was changed, and with the new set of calculations and also with a bit of structural reform, many of the projects were advancing quite quickly. But this is only the single year. It's not showing as a remaining effect for the coming years. So again, it might be a single effort. Let's focus a bit more now on the carried over projects. Here on the slide, you can see 2 things: the number of projects in the annual NDP. It's steadily increasing. So up until 2020, we had not more than 100 projects listed. Now it's over 300. And the share of the projects that are carried over for multiple years. Again, a decade ago, it was relatively high. So somewhere around 80–85% of the projects remain in the pipeline. And the share was dropping. But the reason for this dropping share is that the total number of projects has been steadily increasing. So if you just calculate the full number for each of those years in the past 5 years, you can see that even more projects are being carried over. So it seems like the pipeline is full. and for whatever reason, we are not able to construct all of those investments in Hungary, and this is causing a delay. And if you just narrow it down to the carried over projects, so those few hundred that you've seen previously, this is the different status. You can see which of them are in an advanced phase, which of them are delayed, and which are going as planned. Again, wanting to emphasize that for the right side of this curve, we are having projects that in some cases are not delivered yet. So 2 years ago, they seem to go as planned, but whether it's going to be, the same reality in 2 years, it's something that we can't tell yet. Nevertheless, again, in these years, somewhere around 2020 and 2021, you can see some movements with the different shares, and it indicates some kind of institutional shift. Now let's see the environment. I think most of it is true for all the European countries, or at least some that are related to the economic issues and COVID. But let's just jump into it, how it went in Hungary. So for the last 15 years, we had a period after the financial and economic crisis with low economic activities, a sluggish economy, no investments ongoing, and of course the consumption habits were changing. So we didn't really expect that much change in the external environment in this period. Now for the following 5 years, the state has put a lot of money into building small-scale PVs for residential units, and of course this boom was ongoing for 5 years, and it has significantly decreased the hosting capacities, which of course leads to the need of distribution system development. So again, by the end of this period, we expect the pipeline to be filled with DSO investments and needs. Then we had COVID, of course. It did change the consumer behavior, but actually what we recognize is that the development plans were more or less unharmed by the COVID. Of course, how we expected consumption to be delivered to the consumers changed, but the effect was not really long-lasting. Yet it was also interesting to see that the panic that we had 2 or 3 years ago, how it's going to affect our electricity use, we didn't really realize. And finally, for the last couple of years, we had 2 very important drivers in the Hungarian electric system and also in the economic system. First is that we had the COVID rebound, so everybody was again going to work and trying to produce goods. And also in the Hungarian economy, now we see a rise for constructions with constructing, for example, battery manufacturers, which means that they also require a lot of power. And again, this requires a lot of investment on DSO and TSO side, which means that again, the pipelines are more or less stuck for the last 5 years. So the huge change that we expect based on the external environment is that there is some institutional drift in this period around 2020 to 2022. And if you shoot again the number of carried over projects, you can see that there is an increase of those projects. So the results of the decreasing hosting capacity is really seen. There is a need for network investments, but also delayed projects and advanced projects, and also the planned projects number is rising. So again, in 2 or 3 years, we will see how many of those are going to be realized. But now if we just, let's say, truncate the right end of this figure and say that we also narrow it down to the projects that are already delivered, you would see a share of delayed projects very high because of the lack of manpower and because of the shortage of units to be constructed. Just as an example, let's say 5 years ago, before COVID, if you wanted to build a high to medium voltage substation in Hungary, it didn't take more than 2.5, 3 years with the permitting process included. Now we're talking about at least 6 years, and in some cases 8 to 9 years. So almost triple delivery time is what we see because of the previous reasons that we have said. And of course, we have some expectations for the future. So this year and the coming years, definitely this shortage of manpower and shortage of units is going to increase the network operation costs. We expect it to be skyrocketing. And since the tariff calculation for these regulated entities has a couple of years of delay from previous years, the actual operational costs that are confirmed by the regulator are far below the levels that would be needed to deliver all those investments. Again, despite the fact that we need these investments and these new units, it's definitely not going to be covered by the budget from the regulator side. And again, we believe that this is a typical case of institutional drift, what we have here. So just to conclude, you have seen many data, and we're going to publish it hopefully in a month's time in a preprint and then in journal paper. And you can see that, of course, the schedules are fluid. we see delays everywhere, and we see very different reasons for canceling the projects. But still, we believe that this is, for some reason, part of this institutional drift. Again, remember that the external forces of politics and the external forces of the institutions and their slow tempo to change how they operate is something that is having an adverse effect in this case on network expansion planning. And of course, to finish on a high note, we have some policy implications as well. It was really hard to assemble the database of those 900 investments for very different reasons. But again, just as an example, we had a single transmission line upgrade that was included in 4 consecutive network development plans under 4 different names. So it's really hard to follow how the projects are evolving, and it's not really easing the work of the network development department of the TSO. And the other thing is adaptive planning and the need to anticipate how our environment changes. You don't say to me that if Hungary's politicians saying that we should go and build battery factories and it's not going to increase power. This is something that we know that we should expect, and we must have some reflection to it also from the engineering side that something must be changed in the finances, in the way how the regulator operates in order to fulfill those needs, because otherwise we see many, many delays. And of course, this is going to have an adverse effect back on the economy as well. And finally, just to wrap it up again, to highlight who we are the FASTER Research Group at TU Budapest. We're dealing not only with infrastructure planning, but as Joel has mentioned, with many RDI projects on European and Hungarian level. So we're very happy to be here. And thank you for your attention. I'm going to be ready for the Q&A as well. Thank you.
Thank you very much, Bálint. It was a quite nice presentation and an interesting one. Okay, so I think that we can start now our session of questions and answers. So please, to the attendees, please leave your questions here in the chat. We have a couple of them. We have for Micael for now. Micael, could you please expand on what consists the hierarchical approach? Do you apply a back-forward sweep to iteratively update the shared variables, or is this precisely the decentralized approach?
First of all, thank you for the question. Here, it is not exactly a back-forward sweep, but it sort of resembles a backward-forward sweep. That is, we first start, let me share my presentation, maybe it's easier. Perfect. So essentially here, what we do, we start by determining the range of active and reactive power flow at the point of common coupling with the transmission network. That is essentially, you determine the maximum and minimum active reactive power that the active distribution network can supply, maximum and minimum reactive power, and then we iterate to determine to find these edges, like to refine the edge of the polygon, representing this active distribution network flexibility, essentially. And then we include these flexible operating regions in the TSO's problem. And that is done by inequality constraints, representing the perimeter of this area. In the end, after TSO optimizes the network, communicates back the desired set point. As you can see here, you can see the initial and the final operation point. It communicates back the operation point, and then DSO performs the settlement in the distribution network. So it's a sort of 3-step coordination procedure, actually.
Thank you, Micael. There is another question, by the way, which I think that is linked still. It's, are you using EDMM to decompose centralized problem, or are you instead iteratively running the independent OPFs and sharing the common variables?
Well, essentially both. Essentially, divide the big problem, the whole network, into transmission and separate distribution networks, and then we optimize each one of them separately. And DSOs share with TSO the desired voltage magnitude and interface active and reactive power flows and associated dual variables. And this process continues until both TSO and DSOs reach an agreement.
Okay, thank you, Micael. So Bálint, but the thing is, because if you mirror your study for INESC TEC, I think that the findings wouldn't be that different. So I think you captured what is the issue. Although about the solution, how can we solve this issue? It's a very complex problem, because I was just thinking while I was hearing you, I was just thinking about our experience at INESC. And well, you have two things. First is you need to, because when you work with industry, you need to have a contract, and the contract is fixed in time and with the current context. So this is an issue. There are other issues. For instance, sometimes we had that experience very recently. Sometimes you do the estimate to do the work, the time that you need to do the work, but then the client says, no, I need it this month, so 3 or 4 or 6 months earlier. And okay, you don't want to lose the client, so sometimes you just say, okay, we will try our best, but then you are not able to deliver in the time. But regarding the contract, how do you think it's feasible to have a contract that it's not entirely fixed in time? For instance, a contract that foresees some kind of evolution during the project. So that's my question more directly. So how could we contract something like this that could take into account future context changes?
I can definitely share the Hungarian experiences. So one thing that was motivating some of the changes throughout the years was the reason that many of the investors who wanted to build large-scale solar PVs, now they had to go for an auction, and after they won the auction, they didn't really build the actual PV farms, but still the connection request was theirs to keep. And it was a huge change, and also it was quite a bit of turbulent change. That some years prior, the TSO and the regulator has changed these types of contracts, saying that you are not allowed to hold this connection request for the end of time. But instead, if you are not constructing your own plant after a given number of years, you have to give it back, and it's going to be re-auctioned. So that was definitely something that was, trying to clear the pipeline, and it did in many of the cases. So that was a good thing to see. Where the other, and I believe this is more on the technical side, and also connected to Micael's presentation, that we still rely on constructing grids, constructing lines to the fullest, even in cases when you don't really have a high peak factor, or that you just utilize the maximum capacity, I don't know, 10s or 20s of hours during the year. So we have to be more flexible on the planning side as well. Now, again, we have the obstructions because this is setting standards, how we calculate it. You are not allowed to do this or do that. But definitely, we have started the discussion with the TSO and DSO colleagues in the last 2 or 3 years. How can we involve a bit different thinking in the planning process? Not saying that it should be, standardized or used as a harmonized legal approach, but definitely we see that there is a room for leveraging here. And my main problem with this old way of thinking, let's say, so the traditional thinking, that if we would like to really construct all those power lines, we simply won't have the budget on the long term. Even in case if you see the next 2 or 3 years, I wouldn't bet anything on what's going to happen in 10 years. So by the time we realize all these plans, what we have today, the whole environment is going to be very different.
Okay, I think you can, kind of using some clauses or something like that. I was thinking in a recent problem that we found with a client. which was trying to install a battery in a place where you had already a wind farm and a PV farm together. Well, in fact, there were more than one wind and more than one PV farm from different promoters, from different owners. And they wanted to install a battery, and they talked with the TSO. They had a green light, but then at the end they said, "Okay, but how will we invoice the energy that is produced?" Well, and then the problem started. There were very old wind farms with feed-in tariff still, so other wind farms with that already participated in the market, and PV was also in the market. So the issue is the TSO pays the amount of energy delivered at the point of connection with the network, where they have the official meter of the TSO, and then downstream that meter you have a lot of energy exchanges, and when you put there a battery, it's a big issue, because sometimes wind farms are producing and the battery is consuming, sometimes the battery is injecting and the wind farms are not producing, and invoicing all the correct amount of energy to all the partners was an issue that was not foreseen. So they were already installing the battery when they thought about this issue, and they said, okay, we cannot put the battery, we cannot commission and start with the battery because we need to sort this out. Of course, big delay. So probably 6 months or so. Even the regulator was contacted, so it's this type of issues. Sometimes it's not very easy to foresee, and in some cases it brings very big delays. Okay, but I agree that we can at least to the best of our knowledge include some kind of I don't know, clauses in this contract based on previous knowledge. Okay, so I don't know if someone else has further questions. Let me check Q&A. Guys, you're very quiet today. Okay, from a technology taker perspective, Micael, this is a question for you. From a technology taker perspective, who do you envisage to be the client? HAL-DSO and the TSO of each specific country, or a market managing entity of each specific country, any manufacturer of energy management systems, another entity? So what is the technology readiness level of the proposed solution? So many questions.
Yeah, well, that's an excellent question. I don't know. I don't think this is, something to be adopted, or this is the best coordination mechanism, or whatever you want to call it, to every use case. I don't believe that. And who is the investor in this will be a major question. My idea is that it should be an investment that is shared between the two types of operators, between transmission and distribution system operator. But of course, from a point of view of regulation, there are a lot of loose points to be taken care of here. Honestly, I don't know.
I tend to agree that it should be shared between the SOs and TSOs. Okay, so we are almost on our time. Any other question? Okay, so if not, I would like to thank you all for attending this webinar, particularly to our presenters, but also to the attendees. So Micael, thank you very much for your time. Bálint, thank you very much for your nice presentation. Okay, guys, so have a nice day, and I will see you soon.
Thank you.
Bye-bye.